Metamorphism of Ore Deposits. Metamorphism of ore deposits is a complex geological process that transforms the mineralogical and textural characteristics of pre-existing ore bodies under the influence of elevated temperatures, pressures, and chemically active fluids. This transformation can significantly alter the economic value and extractability of the ore. Understanding these processes is crucial for effective mineral exploration and extraction. Types of metamorphism. Contact metamorphism. This occurs when ore deposits are subjected to the heat and fluids emanating from an intrusive igneous body. The high temperature causes recrystallization of minerals in the surrounding rock, forming a metamorphic aureole. Examples include skarns, which are often associated with valuable mineralization of tungsten, copper, and iron. Regional metamorphism. This type of metamorphism affects large areas of the crust, typically associated with mountain-building events, orogeny. It involves high pressures and temperatures over wide regions, causing widespread recrystallization and deformation of both rocks and ore deposits. This can result in the formation of new mineral assemblages that are stable under the new pressure-temperature conditions. Hydrothermal metamorphism. This involves the alteration of rocks and ore deposits by hot, chemically active fluids, which can introduce or remove elements, thus changing the composition and texture of the ore. These fluids often originate from magmatic sources or circulate through the Earth's crust due to tectonic activity. Processes in metamorphism of ore deposits. Recrystallization. This is the process where minerals change size and shape but not their chemical composition. For example, in carbonate-hosted ore deposits, calcite may recrystallize to form larger crystals without changing its chemical formula. Phase change. New minerals may form that are stable under the new temperature and pressure conditions. In ore deposits, this can lead to the formation of economically important minerals such as garnet, staurolite, or kyanite. Metasomatism. This is a process where the chemical composition of a rock or ore deposit changes due to fluid infiltration. Elements can be added or removed, forming new mineral assemblages. For instance, in contact metamorphic aureoles, the introduction of silica-rich fluids can lead to the formation of quartz-rich veins. Examples of metamorphosed ore deposits. Skarn deposits. These form in the contact zone between igneous intrusions and carbonate rocks. The heat and fluids from the intrusion cause extensive recrystallization and metasomatism, forming calc-silicate minerals like garnet and diopside. Skarns are often rich in copper, iron, and tungsten. Greenstone belt gold deposits. These are typically found in regions of high-grade metamorphism. The gold is often associated with quartz veins and is concentrated by metamorphic processes, including recrystallization and fluid movement, which remobilize the gold into more concentrated deposits. Massive sulfide deposits. These deposits, originally formed at seafloor hydrothermal vents, can undergo significant changes during regional metamorphism. The sulfide minerals can recrystallize and form new mineral assemblages, which may enhance or reduce the ore's value depending on the new minerals formed. Economic implications. Metamorphism can either enhance or degrade the quality of ore deposits. For example, the recrystallization of ore minerals can improve the grade by concentrating valuable metals into fewer, more easily mined locations. However, it can also lead to the dispersion of valuable minerals into less accessible or less concentrated forms, making extraction more difficult and costly. Exploration and extraction. Understanding the metamorphic history of an ore deposit is crucial for mineral exploration. Geologists use various techniques, such as petrology, geochemistry, and structural geology, to determine the metamorphic conditions and history of an ore body. This information helps in predicting the location of high-grade ores and devising efficient extraction methods. For instance, in regions of known regional metamorphism, exploration strategies might focus on areas where fluids have likely concentrated valuable minerals. In contact metamorphic zones, proximity to intrusive bodies would be a key factor in exploration planning. Conclusion. The metamorphism of ore deposits is a vital geological process that can significantly alter the mineralogical and economic characteristics of these resources. By understanding the types of metamorphism, the processes involved, and their economic implications, geologists and mining engineers can better explore, evaluate, and extract valuable mineral resources. Formation of metamorphism of ore deposits. The formation and metamorphism of ore deposits involve a series of geological processes that concentrate valuable minerals into economically viable quantities. These processes can transform the original characteristics of the ore, influencing its composition, texture, and economic value. The metamorphism of ore deposits specifically refers to the changes that occur under elevated temperatures, pressures, and the action of chemically active fluids. Formation of ore deposits. Ore deposits can form through various geological processes, including magmatic, hydrothermal, sedimentary, and metamorphic processes. Magmatic processes, these involve the crystallization of minerals from a magma. As magma cools, certain minerals crystallize earlier than others, segregating into layers. This process can create layered intrusions rich in platinum group metals, chromite, and magnetite. Hydrothermal processes, these involve the circulation of hot, mineral-rich fluids through cracks and fissures in the Earth's crust. As the fluids cool, minerals precipitate to form veins and disseminated deposits. This process is responsible for the formation of many precious metal deposits, such as gold and silver, as well as base metal deposits like copper, lead, and zinc. Sedimentary processes, these involve the concentration of minerals during sedimentation. This can occur through mechanical sorting, where heavier minerals are deposited by flowing water, or through chemical precipitation from seawater. Examples include placer gold deposits and sedimentary exhalative, SEDEX, deposits rich in lead, zinc, and silver. Metamorphic processes, these occur when pre-existing ore deposits are subjected to elevated temperatures and pressures, causing recrystallization and the formation of new mineral assemblages. Metamorphism can enhance or degrade the quality of ore deposits. Metamorphism of ore deposits. Metamorphism involves the transformation of rocks and minerals under the influence of heat, pressure, and chemically active fluids. There are several types of metamorphism that can affect ore deposits. Contact metamorphism. This occurs when an igneous intrusion heats the surrounding country rock, causing recrystallization and alteration of minerals. Contact metamorphism typically forms a metamorphic aureole around the intrusion, where temperature gradients decrease with distance from the intrusion. Skarn deposits are a common result of contact metamorphism, forming at the interface between igneous intrusions and carbonate rocks. These deposits are often rich in tungsten, copper, iron, and other metals. Regional metamorphism. This type affects large areas of the Earth's crust, usually associated with tectonic processes such as continental collision and mountain building. Regional metamorphism involves high temperatures and pressures over wide regions, leading to the widespread recrystallization and deformation of rocks and/or deposits. This process can form new mineral assemblages that are stable under the new conditions. For example, gold deposits in greenstone belts often undergo significant metamorphism, enhancing the concentration of gold in quartz veins. Hydrothermal metamorphism. This occurs when hot, chemically active fluids percolate through rocks, altering their mineralogy and chemistry. These fluids can introduce new elements and minerals or remove existing ones, significantly changing the composition and texture of the ore. Hydrothermal metamorphism is common in volcanic and geothermal regions, where fluids circulate through fractures and permeable rock layers, leading to the formation of rich mineral veins and deposits. Burial metamorphism. This type occurs when sedimentary rocks and associated ore deposits are buried under thick sequences of sediments, leading to increased pressure and temperature with depth. Burial metamorphism typically results in the compaction and recrystallization of minerals, often forming dense, fine-grained metamorphic rocks. Processes involved in metamorphism of ore deposits. The metamorphism of ore deposits involves several key processes. Recrystallization. This process involves the formation of new mineral grains from pre-existing ones without changing the overall chemical composition. Recrystallization can enhance the quality of ore by increasing the size and purity of mineral grains. For example, fine-grained gold particles in a hydrothermal vein might recrystallize into larger, more easily recoverable grains. Phase changes. Metamorphism can cause certain minerals to become unstable and transform into new minerals that are stable under the new pressure-temperature conditions. These phase changes can concentrate valuable minerals or disperse them. For instance, during regional metamorphism, sulfide minerals in a massive sulfide deposit might transform into different sulfide minerals, affecting the ore's economic value. Metasomatism. This involves the chemical alteration of a rock or ore deposit by fluids that introduce or remove elements. Metasomatism can significantly change the composition and value of an ore deposit. For example, the introduction of silica-rich fluids during contact metamorphism can lead to the formation of quartz veins that may host valuable metals like gold or copper. Deformation. Metamorphism often involves deformation due to tectonic forces, which can create fractures and shear zones that facilitate fluid flow and mineralization. Deformation can concentrate valuable minerals into veins and shear zones, making them more accessible for mining. Examples of metamorphosed ore deposits. Skarn deposits, formed by contact metamorphism. These deposits occur at the interface between igneous intrusions and carbonate rocks. Skarns are rich in minerals like garnet, diopside, and wollastonite, and can host valuable metals such as tungsten, copper, and iron. Gold deposits in greenstone belts. These are typically found in regions that have undergone regional metamorphism. The gold is often concentrated in quartz veins that formed during metamorphism, making these deposits economically significant. Massive sulfide deposits, originally formed at seafloor hydrothermal vents, these deposits can undergo significant changes during regional metamorphism. The sulfide minerals can recrystallize and form new assemblages, potentially enhancing the deposit's value. Quartz vein gold deposits. These are often associated with hydrothermal metamorphism, where gold is precipitated from hot, mineral-rich fluids circulating through fractures in the host rock. Metamorphism can further concentrate the gold into high-grade veins. Economic implications of metamorphism. Metamorphism can have profound economic implications for ore deposits. The processes involved can either enhance or degrade the quality of the ore. Enhancement. Recrystallization and phase changes can concentrate valuable minerals into larger, more extractable grains, improving the ore's grade. Metasomatism can introduce new valuable elements, enhancing the deposit's economic potential. Degradation. Metamorphism can also disperse valuable minerals, making them harder to extract. High temperatures and pressures can cause the breakdown of economically important minerals or the formation of less valuable mineral assemblages. Exploration and extraction. Understanding the metamorphic history of an ore deposit is crucial for effective exploration and extraction. Geologists use a variety of techniques to study metamorphosed ore deposits, including petrology, the study of rocks and minerals under a microscope to understand their formation and alteration history. Geochemistry, the analysis of the chemical composition of rocks and minerals to identify the processes that have affected them. Structural geology, the study of rock deformations and structures to understand the tectonic forces that have influenced the deposit. By integrating these techniques, geologists can develop models of how ore deposits have formed and evolved through metamorphism. This knowledge helps in predicting the location of high-grade ores and devising efficient extraction methods. For example, in regions of known regional metamorphism, exploration might focus on areas where fluids have likely concentrated valuable minerals in veins and shear zones. In contact metamorphic zones, exploration might target the margins of intrusive bodies where skarn mineralization is expected. Conclusion. The formation and metamorphism of ore deposits are dynamic geological processes that play a critical role in concentrating valuable minerals into economically viable quantities. Understanding these processes is essential for effective mineral exploration and extraction. By studying the types of metamorphism, the processes involved, and their economic implications, geologists and mining engineers can better predict the location of valuable minerals, assess the quality of ore deposits, and develop efficient extraction strategies.